Okay, so here we go again with a bit more trigonometry. In the last video, we looked at our first identity, which was sine over cos equals tan. In this one, we're going to be looking at some slightly more complex equations, in particular looking at what we call quadratic trig equations. So basically, equations that involve the trig ratios, but can be solved using the same techniques as we've seen here in the course with quadratic equations. So, and along the way, we will bump into the second of our trig identities that we need to be able to use. So, here we go. We've got two equations to solve. So we've got 2 sine squared x plus 3 sine x plus 1 equals 0. The first thing just to point out is when you do writing these, because if we had here, if this thing said sine x squared, it would look like you're doing the angle, then square it, then take the sine of it. But what we actually need is the square of the sine. So which is why notation-wise, you always find that they put the squared sign there rather than after the x. So here we go. What we're going to do, we can treat a trig equation, a quadratic trig, in the exact same way as we treat any other quadratic equation. So what we're going to do is look at this and say, well, okay, can we factorise this? Well, if we're going to factorise it, we've got to have 2 sine x and the sine x there, because that's how we're going to get 2 sine squared x. And then we've got to make this sine x term in the middle, and the numbers in here have both got to multiply together to make 1. So hopefully we're happy with that. And just take a moment just to check that that thing, when you multiply it out and do FOIL, does actually get back to the original equation. And I assure you it does. So if you're happy with that, moving on, same principle as before, two things multiplying together to make 0, either one or the other makes 0, so we can split it to two simple equations. And on the left hand side over here, we've now got sine x equals minus a half, and that gives us x equals minus 30. Now again, we've got the issue that we want our range from 0 to 360, so minus 30 is not the range we want. Little sketch of your trig curve. There's the minus 30, there's the two values that you want, and hopefully by now you should be comfortable working out that that gives us, not that one, but we get 210 and 330 as the two values we want. Over on the other part of this, we've got sine x plus 1 equals 0, so sine x equals minus 1, and so that gives us x equals minus 90, and again we've just got to adjust that, and I said it's just off the graph, but here's our minus 90, so if we come across here, we can see, oh, there it is on the graph, we're going to get 270. And there we go. So there's our solutions. So you're going to get solutions coming from the one side of the equation here, solutions coming from the other side. So it's perfectly possible to get more than 2 solutions. This one's given us 3, but that's only because we've hit kind of 90 degrees here. Normally, you might expect to get 2 from there, but 2 coming from here. So you could get as many as 4 solutions to a quadratic trig equation. So there we go. So exactly the same principles using factorising that we did with your normal quadratics. Okay, moving on. Here's part B, and the issue with this one, again, same as before, when we had sine over cos equals sine, we had to use a trig identity. Here we've got 2 different ratios. We've got cos and we've got sine, whereas in the previous one, it was all just in terms of sine. What we've got to do is take this equation here and express it all in terms of a single ratio. How do we go about doing that? Well, we're going to need the second of our identities. So here we go. Let's have a look at what's going to happen. Okay, so when the slide goes, there we go. Right. So we had previously tan theta is sine theta over cos theta, and that came from looking at that triangle there. And I'll just put under there that we can see that sine theta is opposite of hypotenuse, y over z, cos theta adjacent of hypotenuse, x over z, same setup as before. Now, instead of doing some dividing here, what we're going to do is take another fact we know about this triangle, which is that statement there, which we all know as Pythagoras' theorem. I'm going to take that, and what I'm going to do is divide the entire equation by z squared. So on the left-hand side, we've now got x squared over z squared plus y squared over z squared, and on the right, clearly z squared over z squared, which is 1. And what I've done is just kind of slightly rewritten these ones here, so we've got x squared over z squared, that's just x over z all squared. And here comes the groovy part, because hopefully you should spot that x over z, yep, is cos, and y over z, what do you know, that's sine. So what we've got now is cos squared plus sine squared equals 1. So it's well worth just kind of pausing the video for a second and you can just grab your calculator and just, if you just hit, I don't know, just pick any value, do the cos of it, square it, same to sine, and just check that for any value you could possibly pick, that statement there holds true. And you'll find it will do. So what we get is our next identity, which is that sine squared theta plus cos squared theta equals 1. And that is the thing that's going to allow us to solve our equation. So here we are back with our equation, 4 cos squared plus sine squared equals 1. So that's what we've got to solve. And what I'm going to do is a little bit of scribbling and rearranging over on this right hand side of the page, because we've now got, that's my version of saying sine squared plus cos squared equals 1. And what I want to do is effectively replace this cos squared. So I'm going to make my identity say cos squared equals. Simple enough. So cos squared equals 1 minus sine squared. And so now what I'm going to do is replace that in my original equation, so it ends up looking like that. So that's allowed me to get the entire equation just in terms of one ratio. In this particular case, it's just in terms of sine. All we've got to do now is multiply out the brackets and do some rearranging, and we end up with a quadratic. There it is, 4 sine squared x minus sine x minus 3 equals 0. And now we can proceed in exactly the same way as before. So factorise and take the two parts of the equation. There we go. On that side we've got 4 sine x plus 3 equals 0, gives us sine x equals minus 3/4. So that's minus 48.6, but again, not in the range. So we've got there's our good old sine curve, where the other value is going to be. And again, hopefully more than familiar by now, that bit's 48.6, so that's 48.6. And that bit there, that's 48.6. So you should be able to figure out the other two values, 228 and 311. From the other side of the equation, again, we've ended up with sine x equals 1, so x equals 90. So there we go, there are our three solutions. Now, both equations that we looked at were you were able to factorise them, but there's absolutely no reason why, if you get an equation that doesn't factorise, you can't use the quadratic formula. And when you're using the quadratic formula, all you do is you say, instead of x equals minus b plus or minus, etc., it's sine x equals minus b plus or minus. And on to the last example I'm going to do, which is this one. Now, this one doesn't look particularly like a quadratic, but we can use similar principles, and there's a kind of a bit of a twist and tell, so you've got to be a bit careful with these kinds. So here we go. Off we go. Previously we said that you need everything in terms of one ratio. Well, technically speaking, you don't with this one, because what you can do is say, okay, well, if I've got that, I can simply factorise it. So take out sine x, and we've got sine x coming out of that first term, gives us 3 cos x, and then the minus 2, so there it is factorised. And now what we've got is the same principles we had before for solving a quadratic, because what we've got is two things, that thing, and the bit inside the bracket, two things multiplied together to make 0. So that means either sine x equals 0 or 3 cos x minus 2 equals 0. So we're really making use of exact same principles, but in a kind of non-quadratic-y type of a way, if that makes any kind of sense. So here we go. From there, sine x equals 0, so x equals 0. And that's that one. And we've got two other values, but here we need to pay very careful attention to the range of values we want. So if we have a look up here, that thing there is saying greater than minus 180, and this one's saying equal to or less than. So what that means is that one is not in the range, so just the two values that we want are just 0 and 180, and then on the other side we've got cos x equals 2/3, so x is 48.2, there's my cos curve, and then I've just drawn it kind of in between minus 180 and positive 180, so that's why my cos curve looks a little bit different from what you might be familiar with before. And so our two values, there they are, and it turns out that's 48.2 and minus 48.2. And away you go.